But now I'll pass you along to Fraser Tweedale from Red Hat, giving his presentation on network-bound encryption with Tang and Clevis. If you want to read Fraser's bio, you can again use the app to do so. If you can give him a warm welcome.
So, good afternoon. I know this is the last session and probably half of you either have full brains and the other half just want to go get beer. So, yeah, thank you for coming to my session. Yeah, I'm a software developer at Red Hat, so I'm definitely not on sort of the business and risk side of things that is quite prominent here at this conference. So I do feel almost like a fish out of water, but it's good to be here and get these other perspectives on security technology. I'm going to talk to you about network-bound encryption and some interesting tools we're building around that at Red Hat. So let's start with a story, and the story is the story of a hard disk. This hard disk lives in a employee's workstation, a laptop computer, or maybe in a data center, and this disk has full disk encryption. So it has volume encryption keys on it, and when the machine boots up, a passphrase needs to be supplied in order to decrypt the volume and continue with the boot. And so we've got a bit of a management problem here, because every time the user boots up their computer, they need to go and key in this passphrase. This is obviously a step that must be performed every time, depending on how often they boot their computer. Hopefully not too often, but depending on the operating system, you might need to reboot it more or less frequently to apply critical system updates. In a data center, again, you're not going to be rebooting your systems particularly frequently, but they might need to come up again because you've had critical system updates to apply, or the kernel's panicked or whatever. So you need to get a decryption passphrase to this system. So in a data center, this can be over a lights out management system, or as a last resort, someone physically at a terminal keying in a passphrase. For your user, it's something they have to do every time you boot the system. The advantages of full disk encryption, of course, is that if the machine needs to be sent off for warranty service or is decommissioned, you don't need to worry about the security of that data. But most of the time, the disk is going to be used in a secure context. The employee is at the office, or the disk is in its usual rack in the data center. So it would be nice if there were ways to automate the unlocking of disks. So another common use case for decryption of secrets is TLS private keys and other secrets used in your network applications. And once again, these need to be supplied not at server boot up time, but the boot up of your server software. So, as a basic example, you bring up the Apache web server and it prompts you, please enter the passphrase for your private keys. So again, there's a management overhead here, and ideally, we'd like to automate that away, but also have our secrets encrypted at rest. It's quite common to see advice on the internet. Don't have to look far on Stack Overflow to find someone asking the question, every time I start the server, it's prompting me to enter my password, and if my machine gets rebooted or something, I just want it to come back up. And usually the advice is something like, well, just run this OpenSSL command, and the result is that the keys are just sitting there on the disk in the clear, which is poor security hygiene. And then our old friend USB. So USB drives containing potentially sensitive corporate information being taken home by employees is an issue, and it's something that many organizations have to be concerned about, whether the exfiltration is malicious or merely negligent. And of course, the flip side of the USB scenario is people bringing in USB sticks from outside the organization containing unauthorized software, malware. They've picked it up off the footpath outside the building and thought, oh, this looks interesting. Let's take it into the building and plug it in and see what's on it, and then you're hosed. So it would be nice if there were ways to encrypt the data on the USB disks in a way where they can be used securely within an organisation transporting data around. Something that many people are quite used to doing. I've got to get this big file from my system over to Bob because Bob needs it. Just plug in a USB stick and throw it at Bob. So we want to still enable these use cases, but ensure that the USB volumes are useless when taken outside the organisation, and also to prevent unauthorised volumes being used within your organisation. So these are some use cases that we're looking at developing solutions for at Red Hat, and right now I'm going to jump into a demo of the software that we've been developing. I've worked a little bit on it, but I'm not the main developer. And this software, what you're going to see in this demo, specifically addresses the full disk encryption use case. Okay, so on the left, we have it's a virtual machine, but it's got an encrypted disk. So I've booted it up, and it's currently prompting me for the passphrase to unlock the volume keys and continue the boot. So I'm just going to enter the passphrase. Over on the right, this is a server. It's on the same network as the client on the left. And I'm going to set up some software on this system. So it's a server. The software is called Tang. So the software is installed. If we just have a look at the RPMs. Is this big enough for everyone, by the way? Can anyone not read this? Okay. So the package is called Tang KeyD. It contains a number of binaries, one of which is Tang KeyGen, which we'll use to generate a couple of keys. We need to specify an elliptic curve group. There's a few supported groups, and don't worry too much about these details. We're going to advertise the key, and it's going to be a signing key. Okay, Tang KeyGen -A-S. Demo gremlins. Maybe I need to. Okay, that's better. I just blew away a directory earlier. Okay, so we've generated a signing key. We also need to generate what's called the recovery key. And then we can start the server. So we'll say system control start Tang key daemon .socket. So we can see the socket for this server is listening. It's a socket activated process. So the service itself is not actually running. Over on the client, we can see that the boot is completed. So I'm now going to log into this system. And just fire up a terminal. Okay, and over on this system, if we have a look at the LUX headers, so LUX is the Linux Unified Key Setup disk encryption system for Linux. So if we do sudo crypt setup LUX dump and the name of the disk, and we'll just grab a slot. Whoops. That should be dev. So we can see that there are 8 slots in the LUX header. Only one of them is in use, and this is where the encrypted passphrase is. Or the metadata that can be unlocked when I type the passphrase containing the volume keys. So what we will now do is we'll run the Tang LUX bind command. So I need to do this as root. Again, we'll specify the device and the host name of the Tang server, which is f233.ipa.local. Tang LUX bind. What on earth is this doing? Always with the demo gremlins, eh? Tang LUX bind. Get address info. Just bear with me while I try and work out in approximately 10 seconds what's happening here. Always with the gremlins. Sudo tang explained -d video 2. Well, this is a problem. Is the server running? Oh, the service failed to start. That's a problem. Golly gosh. Okay. Well, always the demo gremlins, eh? Suffice to say, I'll talk you through what will have happened. Should the binding program have run successfully, and should the server have started successfully, of course, in the first instance, we would have been prompted with the question, so it'll print out a key fingerprint of the server's signing key, and it will ask, do you wish to trust this key? So it's a trust on first use scheme, or TOFU, if you're familiar with that abbreviation. Having trusted the key, it will perform some computations using the client's private key and the server's public key, and then use the result of that to encipher the secret. Store that data in the LUX header. Then I would have rebooted this system, and presuming the Tang server on the right-hand side was still running, the boot prompt to enter the passphrase will have come up, but whilst waiting for me to enter the passphrase, in the background, in the boot environment, the client will be communicating with the server and executing the Tang protocol. And should that execute successfully, it will reveal the key encryption key, and then the boot will complete without operator intervention. So the idea here is simply that we want the systems to come up when they're in a secure network where the Tang server is available over the network. In that environment, the client will come up automatically. And I really do apologise that this demo is not working. Honestly, it was all going fine, you know, this morning and yesterday, and I regret that it's not working. But if you would like to see the demo working, come and find me. I am around for the rest of the conference, and I promise to get it going again. Okay, so that is the unsuccessful demo concluded. So let's review what we would have seen had the demo worked successfully. We would have seen simple provisioning of encryption for secrets at rest in this particular example for a disk encryption key. Automated decryption when the Tang server is available, and when the Tang server is not available, we just fall back to the existing method, so a user inputting a passphrase. The terminology we use here is that the secret is bound to the network, because the automated decryption capability is only available when it can communicate with the Tang server. The final point, the server never leaving the client, is not something that is apparent from the demo, but in this protocol, the secret is only ever learned or known by the client. The server gets no information about it whatsoever. So in this sense, it's quite distinct from key escrow, has very good privacy guarantees around it. The security assumptions here, of course, are that the Tang server is only accessible from the secure network. If it's globally accessible, then you lose the ability to prevent the disk from being unlocked if it's been taken out of the premises, or you've decommissioned it, someone gets a hold of it. If they can access the Tang server, then of course they can decrypt the disk. So this is a security assumption with this software. And of course that the secrets and the keys are safe in the client's memory. But if your client is compromised in that way, you of course have big problems, and Tang won't save you. So Tang is a protocol based on Diffie-Hellman exchange, and if I have a show of hands in the room, is anyone familiar or was once familiar in university with Diffie-Hellman exchange and how it works? Okay, so Diffie-Hellman exchange is a key agreement protocol where two parties with their public and private keys can be public, private are kept to oneself, These two parties can agree on a shared secret for the establishment of a secure communications channel, but an eavesdropper, Eve, cannot learn the shared secret. There's an encryption scheme, well, there are a few encryption schemes based on Diffie-Hellman. One is the integrated encryption scheme, where this shared secret is used as the input to a key derivation function to derive a symmetric key of a particular desired length, and that symmetric key is used to encipher a message. So on the one side, Alice, given Bob's public key, can encrypt the message to Bob and transmit the message, and then Bob is able to compute the same shared secret and derive the same symmetric key using the information he receives from Alice and decrypt the ciphertext. But again, an eavesdropper is unable to obtain enough information to decrypt the message. So the new cryptography used in Tang is the McCallum-Raleigh exchange. So this is due to Nathaniel McCallum and Robert Raleigh, who are both employees of Red Hat. And that URL there is the original posting to the cryptography mailing list. So the algorithm is public, and in a couple of slides I'm going to take you through it. The intuition of McCallum-Raleigh exchange here is that Alice encrypts a message to Bob's public key, but does not send it to Bob. In order to decrypt the message, Alice has to ask Bob to encrypt an ephemeral key with Bob's private key, and then the response from Bob can be used to recompute the original secret, rederive the same symmetric key, and decrypt the message. So it's about Alice encrypting a secret that only Alice knows, and Alice in the future can decrypt that, but Alice requires the assistance of Bob to do so. Bob cannot learn anything about the secret, and also neither can an eavesdropper. So, caution, math ahead. It's only a couple of slides. I promise if this causes you pain, it won't last long. So, the parameters for McCallum-Raleigh exchange are much the same as for Diffie-Hellman. We need a cyclic group of order n with a hard problem, such as the discrete log problem, or the analog to discrete log, which is an elliptic curve point factorization in elliptic curve groups. There's a generator, which is just an element of the group and is public, a key derivation function, a symmetric encryption algorithm, and by the way, for these two in our implementation, we use PBKDF2 and AES GCM, which is the Galois counter mode. But again, you can choose any secure KDF and symmetric cipher. And the message M to be encrypted, which will be a key encryption key, a TLS private key, these sorts of things. So the secrets you actually want protected at rest. So in the encryption phase, Alice generates a private key, which is an element of the group. Bob also generates a private key. Alice can generate a private key separately for every secret that needs to be encrypted. The server's private key is persistent, so it doesn't change over time. In order to encrypt the secret, all the client needs to know is the server's public key. This can be obtained in what we call an advertisement request. So the client asks the server, what are your public keys? Or it could be distributed in some sort of base image or corporate standard build image or whatnot. So it doesn't necessarily involve network communications for the provisioning phase. So given the server's public key B, Alice computes this secret G to the A, B, the group generated to the power of A times B, two private keys. And then that is the input to the key derivation function, and then that is used to key the symmetric cipher and encrypt the message. Alice stores Bob's public key, her own public key, and the ciphertext, and crucially, discards her private key and the symmetric key. So this ensures that in the future, without the help of the server, there's nothing that can happen on the client in order to decrypt that secret. So for the decryption phase, or the acquisition phase, the client generates a new private key X, again just an element of the group, and then calculates this value X, which is her public key multiplied by the public key corresponding to the ephemeral key X. Transmits that to the server in what we call a recovery request. The server enciphers that with B, the server's public key, which you'll recall is persistent, so the server remembers its public key and private key. And then this value X prime is returned to the client, and then X prime is used in this computation to recover the original secret G to the AB, and running that through the key derivation function. Once again, we get the same K as was used to encipher the message, and then this can be used to decrypt the original message, which is the secret you want protected at rest. Okay. So that's the cryptography that's in use in this protocol. Okay, so the implementation, it's a server-side daemon, so that's the Tang key that we saw in the demo. That didn't come up because reasons I need to investigate. And there's a Clevis pin. We'll get to what that is in a few slides. It's written in C, has minimal dependencies. The only dependency is OpenSSL, which we use for the ASN1, which is what the wire protocol uses, and for the elliptic curve cryptography. So we don't use any TLS or anything like that. And it's small, so the implementation's quite small, and it's very fast. The protocol, as I mentioned, uses ASN1 objects, serialized using the distinguished encoding rules. The packets are UDP. There's no encryption in the channel because you don't need it. And in its current incantation, it's trust on first use. So you would have seen, had the demo worked, in the demo, the prompt, do you wish to trust these keys? However, it's entirely possible to implement key pinning. So you could, for example, distribute the valid key fingerprints in your corporate standard builds, or other offline provisioning methods. Or you could store them in DNS using DNSSEC and have records that are the fingerprints of the official Tang servers in your organization, for example. So you can, in this way, potentially avoid having to prompt the user and say, do you please check this fingerprint, is it correct, yes or no? Why is it important to do the fingerprint checking? It's because if you get man in the middle during the provisioning phase, or someone masquerades as the Tang server, then it could cause the client to encrypt to a bogus or a non-existent recovery key, which essentially means that that secret will be lost for all time, and the client, if it's full disk encryption, is just DDoSed itself forever, unless you remember the passphrase. A running Tang server is also a live DOS target. And importantly, the security of the protocol depends on not being able to guess the ephemeral key X. So if you are using Tang for full disk encryption, you want to make sure you have enough entropy when you go about initiating the Tang recovery stage of the protocol. Because if you can guess X, then the security breaks down. Also, this is all the algorithms that we're using. The public key algorithms are vulnerable to Shor's algorithm. So, if we see practical quantum computing in the next 10 or 20 years, then this protocol will be broken in polynomial time. So hopefully we can find quantum computing resistant algorithms to use instead by then. So mission accomplished, right? We've succeeded in having our automated unlocking of secrets when on a secure network, so when they have access to the Tang server. But we're not really there yet, because one Tang server is not really going to be very resilient. It's at the end of the day one piece of a larger puzzle. And if we're going to bind secrets to Tang servers on a network, what other kinds of things might we want to bind secrets to? So the first one, obviously, which is not on the list, is users' passphrases that they remember. So you use a key stretching function based on or applied to user input to to get some sort of secure secret, assuming the user has a good passphrase, which of course is, as we know from many talks today and usually not a valid assumption. We also might like to bind to a trusted platform module chip, so you seal secrets in the TPM so that your disk is bound to some physical machine or some machine state. We might want to bind to smart cards with crypto processors in them, so a user has to plug in their smart card in order to get access to a secret. And then potentially we can derive secrets from biometric data. You might want to have some master unlock key for a user that gets escrowed in your organization. So when they first come on board and their equipment gets provisioned, we have a master unlock key that gets escrowed, and then if that person gets hit by a bus or leaves the organization and you're left with a disk and you say, well, how do we get back into it? You could potentially use a master key kept by your organization. And so we get to the point where we make the observation that security, it's not a binary thing. It's not like you're secure or you're not secure, but it's a sliding scale of risk but convenience on one end, and security but less convenience or outright inconvenience on the other end. And where to position yourself on that spectrum is going to be different in all kinds of different organizations or sub-organizations. And the policies for disk unlocking or secret unlocking should be driven by business requirements and not by the technical capabilities or limitations of the technology. As a completely made-up example of an unlock policy that you might want for a user's workstation, you could say, okay, well, I want either their passphrase or a Tang server on the network if they're physically at an office, or their smart card, or a secret derived from some biometric data like a fingerprint. So you say any two of these is good enough. So that's stage one. And then at the next stage, you say, well, and we want to make sure that the disk is plugged into the computer that we gave them, to the physical machine that we gave them. So we're going to bind to the TPM. And in this case, we want the result from stage one to be true. Yes, it's good. We'll let them in. But then also the TPM. So we need both of these, threshold of 2 out of 2 possibilities. And then finally, at the lowest level, we say, okay, well, we want either a yes from stage 2 or some master passphrase that we escrowed when they came on board, and we'll pull out as a last resort if we need to. So we've got sort of this nested unlock policy where we have thresholds involved, and this, it's a contrived example, but you can see how you might want to implement a policy like this in your organisation. So we want to make that possible for people to do. So there's an algorithm called Shamir's secret sharing, which is basically a secret splitting algorithm, where you can distribute as many shares in a secret as you like and require a threshold of k of n secrets to come back to you in order to be able to get at the secret. The intuition of Shamir's secret sharing, again, comes from math, and the observation that k points describe a polynomial of degree k minus 1. So to describe a linear function, you need 2 points. 3 points describes a quadratic, and so on. So in Shamir's secret sharing, you randomly pick coefficients in your polynomial of degree k minus 1, where you want k to be the threshold. You distribute points on this line to people who are to hold shares in the secret. Crucially, you do not distribute the value of the function at 0 because the free coefficient is set to the value of the secret. And then given k points, you can compute the Lagrange polynomial to recover the secret. So as an example, this is a cubic function, degree 3. So 4 shares are required to recompute the secret. The secret is minus 3 here on this black line, so the value of the black line at 0. And there are 4 points distributed here. These are the coloured circles on the other lines. The 4 coloured lines are what's called the Lagrange basis polynomials. And basically, you compute the 4 basis polynomials given the 4 shares in the secret. That allows you to interpolate the original polynomial, and then you just get its value at 0. Practically, in practical implementations, this is all done in modular arithmetic. But this is the intuition behind it. And so I also have a demo of Shamir's secret sharing, and hopefully this one does work. So I have a Tang server running on this host, and this is the Clevis tool, so this is where Clevis comes into it. So I do Clevis provision. I'm going to provision a secret, -o for the output file, clevis.json, and -p for a pin specification, and we're going to specify a password pin, and it's going to ask me for a passphrase, and I'm going to type that in. It's then giving us the secret, so Clevis has actually generated the secret itself and told us what it is. This secret's now encrypted, but we go and we use this secret to encrypt a TLS private key or a disk encryption key. For the acquisition, we simply provide this same metadata file, the metadata or the Clevis configuration. I'll just show you that. So if I pretty print the clevis.json, you can see it's got information about which KDFs and ciphers are used, the type of the pin that was used, and the ciphertext containing the secret. So if I do an acquire, handing it back that same configuration, it's going to prompt me for the passphrase again, and if I fat finger that, it's going to not give me the passphrase, and if I type the right thing, it's going to give me the same secret that was originally spat out. So the secret that was provisioned is the secret that it yields. So this is a very simple Clevis policy, but let's do something a bit more sophisticated. If I use the Shamir's secret sharing type, that allows me to specify an additional layer of nesting, so additional pins, as an array of nested Clevis pin specifications. So here I'll have another passphrase pin, and then I will also have a Tang pin, and I need to give it a host name. And I'll just talk to the Tang server running on this host. And finally, I need to tell it what the threshold is. I want a threshold of 1, and I am missing a square bracket here. Okay, so it's going to do 2 provisionings now. One is the password provisioning that we saw a moment ago, and the next one is the Tang provisioning. Here is the trust on first use. Here's the fingerprint. Do you want to trust it? I say yes. And it's provisioned the secret. Now if I kill the Tang server and run Clevis acquire, giving it the clevis.json, it's prompting me for a password, and it's also trying to talk to the Tang server, but the Tang server is not running. So I need to put in the passphrase, and it's going to give me the secret. If I fire up the Tang server once again and attempt the acquisition, it's going to prompt me for the passphrase, but also in the background, it's talking to the Tang server and has completed the Tang recovery and unlocked the secret because the threshold that we specified was 1. So this is the sort of thing that you would have seen in the full disk encryption example if it was working. Reviewing what we just saw there, Clevis is client-side pluggable key management based on Shamir's secret sharing. Plugins are called pins. We have Tang and password plugins, and the sky is the limit in terms of what you could write. JSON configuration, and it's written in C with minimal dependencies. The history of these projects, basically early last year we started the DAO project. It was using X509 for authentication, and also the encryption certificates were X509. And in this protocol, the client sent a blob to the server decrypted it, thus learning the secret, and sent that back. So this didn't have the privacy characteristics that we wanted. In around September, Nathaniel McCallum had an insight and thought, well, maybe we can use something based on Diffie-Hellman. He worked with Bob Rallier, and the outcome of that was the McCallum-Rallier algorithm that I showed slightly earlier in the presentation. And then in December, we realized that we were actually trying to solve two different problems here, so we split the project into Tang and Clevis. The LUX integration is currently only supporting Tang, so we don't have support for arbitrary Clevis policies for LUX integration yet. We're working with the LUX developers and we're hoping that LUX version 2, which is going to be designed to be more extensible, will have support for richer Clevis policies, but that's only in the very early stages at this time. Integrating with USB guard, so this is designed to satisfy the use cases that come from that story at the beginning of the talk with the USB sticks, so using them securely in the organisation but taking them out of the network means that you can't access what's on the volume, and also locking down the systems with policies that say only Tang provisioned USB storage volumes will be allowed to be mounted on our systems. So yes, the USB guard integration, which is in the early stages at the moment as well. For the Tang server and protocol itself, we're currently looking at the key rotation possibilities. So the fact that we have the signing keys is what's going to make that possible. So you can generate new signing keys and new recovery keys, change which ones are advertised, and over time migrate away from older keys to newer keys. And also looking at what people who are going to hopefully install and run this in the organisation expect of the daemon and the clients in terms of logging. So what do they actually want to know for audit purposes? If I had time right now, I'd be working on a TPM Clevis pin and Let's Encrypt integration, because I think Let's Encrypt is an excellent initiative, but currently it just splats all of the keys onto the file system in the clear, which I definitely don't like. I've played around with Apache integration for Clevis, and I have a blog post on that. It's fairly ad hoc, but you know, it does work. Availability, so currently we have some unofficial package repos with the Tang software. We don't have any packages for Clevis. The source code for both projects is GPL v3 up, and it's available on GitHub. We're hoping to get the Tang bits into Fedora 24. You can help by doing review of the crypto if you're a cryptographer, protocol review and code review. If this stuff interests you, please try it out. And talk to us about your use cases. So if you think, oh, we might have an application for this, but maybe we haven't considered it, or I didn't talk about it today, please let's have that conversation. And contributing Clevis pins. So if there are interesting sources of secrets that you think would be worthwhile supporting in Clevis, then the pin interface is fairly straightforward. If you know C, you can write one. So that's the end of my talk, but one final point on the terminology. The terms come from a kind of shackle called a Clevis shackle. So the Clevis is the shackle and this is the Tang, and pins are the bits that hold it all together. So that's where the project's terminology comes from. So questions, hopefully we have time for one or two.
Yeah, we've got a couple of questions. Firstly, how would you deal with client hardware failure?
Right, that's an excellent question. We don't have anything in particular to deal with that. I mean, if the disk crashes and crashes hard, you're going to lose that data no matter what. So, yeah. Yeah, for sure. Then you can mount it into a separate motherboard and do it. But then, you know, in the future, if we have TPM support in there and you're physically bound to the TPM, well, that's going to be a bit harder. So, of course, having an appropriate backup regime is important as well.
One more question. Is 2016 the year of the Linux on the desktop? I was going to say, Darren should probably know better because he knows that 2010, 2011, 2012, 2013, 14, 15 were all year of the Linux on the desktop. So.
Well, I'm going to go ahead and answer that question in the affirmative because I plugged into this projector and things worked. So, yeah, I think it's arrived.
Okay, cool.
Okay, thanks for listening to my talk.